What's going on, developers and creators out there? I'm Erickson. In this not so basic FPGA tutorial video, we're going to be looking at how DSP algorithms can be optimized on FPGA. I mean, this can be a piece of cake for some people. This might be advanced for other people. So it's definitely not a beginner kind of tutorial though. In the last couple months and years, I've been learning about the art of implementing DSP algorithms with my FPGAs, and I've learned so much that I've been applying so much of it lately. And I looked through the web, see if I can find a simple, straightforward an algorithm that I could use to demonstrate this idea of optimizing your design on FPGAs. And I came across this video right here. This video by Mr. V, I'll just go by Mr. V. I'm now going to attempt to pronounce this name, not to disrespect a very creative channel. Thank you, Mr. V, for taking your time and putting this together. On this video, Mr. V now goes over a image processing algorithm, specifically neighborhood processing algorithm, which is very practical and and used a lot in image processing. I mean, I'll quickly go over the concept, but not in details. The main idea of neighborhood processing is to apply some sort of processing on an image. Let's say here are just a bunch of what they call kernel image processing, or filters, which can be applied to images and totally change the output of the image. For example, this one is used to identify, this one is used to detect edge, and this one is used to blur an image. This is just a couple examples, and this video actually uses this one. So if we go back to this video, we'll see that we have an image here. Let's say an image, a couple pixels, and we see this shaded area right here. What neighborhood processing does, it looks at neighboring pixels of a pixels. In this case, it would be a neighboring pixels of this pixel, and it will apply the kernel to compute a new value that gives you a different output image. For example, if we take the blurry filter kernel, we'll multiply each surrounding pixel, which will have a 3x3 pixel, and the kernel is also 3x3. And we're going to multiply each pixel by its corresponding kernel element and multiply the result. And this will give us this pixel over here. As an example, this pixel will be multiplied by this kernel element right here. The next one, this one will be multiplied by this one, so forth until you go over the entire pixel, the entire matrix. And this is done for the entire image. And what happens next, you would shift this matrix over by 1 pixel and compute the value of this pixel. And this is again done for the entire image. Now let's look at this from a flowchart or diagram point of view. So you have a bunch of pixels. In this case, I'm only looking at 3, but you could have more. In the previous example that I just explained, we have 9 kernel elements, or that means you'd have 9 pixel elements coming into this algorithm. I just used 3 to simplify how I just explain this thing. So basically, you have 3 pixel coming in being multiplied by kernel elements. So you have 3 kernel elements, and the result data is added together and produced the output. This is pretty much what happens in this algorithm, and I'll show you how Mr. V designs his algorithm, and this is how he does it. And I'll quickly explain what's different between this one, what the difference between this one and this one, which is pretty much the pipeline registers. But if we look at the general overview of this diagram, you can see you have your input pixels coming in, here are your kernels, and the data is summed together. You only have these extra boxes, which is in FPGA are clocked elements, and they're called pipeline register, which is simplify how things are implemented in FPGAs. So we have about 3 of them. So the input data is registered, and the register data is multiplied by the kernel coefficient, and the coefficient is registered here, and all 3 kernel multiplication is registered in these registers and edit together to produce the output. So now let's look how can we optimize this design to work on FPGA. This will work. This is how what Mr. V goes with, and it's totally fine to have this implemented on FPGA, just a pipeline and then the entire chain of data together. But this is limited to what sections of FPGA this can be implemented on. We'll look at this in a few seconds. But to optimize this design, we'll need to restructure, completely redesign how this thing is implemented. But functionally, it remains the same. And again, it's totally fine if timing and space is not a concern. This is totally fine. You go with it. Be happy with this design and you move on. But if you're into optimizing this algorithm on FPGAs, you want to use dedicated resources to implement a design. I'll show you how this can be done using this algorithm as an example. So to understand this, let's look at this. Not that omit. Where is it? Let's look at the layout. This is a drastically simplified architecture of the FPGA, Xilinx FPGA layout. You can see that it's composed of configurable logic blocks. It's composed of what they call DSP blocks, digital signal processing blocks, memory, and others. We are particularly concerned about implementing this logic, and we want to see which part or which section of this FPGA we want to implement it on. Looking at this algorithm as an example. Again, configurable logic block, you can implement pretty much anything. Adders, multipliers, AND gate, and other combination logic. Now, multiplier is composed of a specific element that is targeted for a specific application. Let's look at the details about the DSP block in a Xilinx FPGA. This is a DSP 48 block in Xilinx FPGA, and it's composed of adders, pre-adders, post-adders, and a multiplier, and a bunch of pipeline registers. This is pretty much what's in a single DSP block, and the idea is to make how the algorithm use these resources rather than using using configurable logic blocks, or CLB. I'll be referring to them as CLB for algorithm implementation. So the idea is to use these blocks, which have what we're looking at, which has adders, multipliers, registers, to avoid implementing our design on CLBs. We're going to use CLBs for other stuff and use these dedicated blocks for the stuff that we need. And again, if we implement this algorithm as shown here, we're not going to be leveraging those DSP blocks to implement this. The main reason is because of this multiple input adder, and there might be other reasons, but I haven't looked at them at all. I'm showing 3, but again, previous example demonstrated 9 kernels, so you have 9 input adders. And if we look at the block diagram for the DSP blocks, we don't have a 9 input adder. We have 2. I think this is a 3 input adder, but we can call it 2 input adder for now for the DSP 48. So we only have 1 and 2 input adder. None of them are 9 input. So we could implement this. We cannot implement this directly. So we have to restructure the design in order to leverage from those DSP blocks. And I'll go over some of the solutions that I looked at. First one being this one. This one is, again, so similar to the previous ones. Functionally, in terms of functionality, it's the same, but in terms of structure, how it is implemented is different. The goal is to leverage from those DSP blocks and avoid using CLBs for this algorithm. Again, you have your 3 input pixels coming in. You have your pipeline registers. We're just going to look at this one for now. I'll get to the additional boxes in a few. You have your kernels that are used for multiplication, and again, set up for pipeline registers. Now here, this is drastically different implementation. Here you can see you have multiple adders instead of a single adder. So again, we don't have multiple or more than a 9-input adder in the FPGA, we're gonna have to figure out how to get this to be a 2-input adder, and this can be done this way. And the way it's done, you use a bunch of adders, 2-input adders, cascade them together, and adapt your algorithm around this structure. So the way this is done is you have your data coming in. The addition, the output result from this one gets added with output result from this multiplication, and so forth. If you have more kernels, it will just proceed the same way with more adders. And the main idea here is that the structure now uses direct DSP block rather than other resources in the FPGA. So if you look at this single row, single column here, you have your data register, pipeline register, a multiplier register, and an adder. If we go into the DSP block details, if I can find the tab, here it is, you have multiplier, adder, and registers. Look at that. So we have what we're looking for in order to implement this into a single DSP block and avoid CLBs. Golden. And this can be done for the second, the third, and so forth. But in order to get this algorithm to work now, we have to add more registers. And the reason we have to add more registers is because in the previous design, the delay were just the same. So you have your input pixels coming in, same pipeline registers, delayed exactly the same until they are summed together here. So they flow through this chain simultaneously in time to be added here in order for you to get the correct output. But not the case here, where you have your input comes in, it gets added here, the second pixel comes in, it gets added here, but by the time you get to add this previous result with this one, you're not using the exactly correct pixel, which leads to incorrect output. This will not work, and that led me to add delay registers. So I call this the pipeline register, and these are just a bunch of delay registers that gets inserted into a pixel, into the input data, in order to get the correct addition and multiplication at the end of the chain. But this is not scalable. Let me explain the reason that being. If I have 3 pixels, the first one doesn't need delay, the second one will be delayed, the second one will be delayed by 1, the third pixel will be delayed by 2 registers, so you can get a correct output. But this isn't scalable, because if you have if n is 20, the 20th pixel input data will have 20 delay registers. But look at how the amount of registers that is built up once you scale this up to a more number of input data. So this is not a good solution, because we're actually defeating the purpose of optimizing design, because of we're using way too many registers to implement this algorithm. So this is totally trash, not a good solution. So let's look at a second solution used to optimize this design. So the second solution actually came from another video by what's his name, Dr. D. Again, out of respect to Dr. D, Mr. D. I will not try to pronounce his name. He took his personal time to put together this wonderful tutorial video on efficient implementation of DSP algorithms on FPGAs. So let's look at this one. This one that he's talking about here is called transposed FI filter structure. Again, beginners, I'm sorry, I'm not going to go into details. Other DSP algorithms for FPGA do explain how this transposed FI filter structure work. But in this video, the goal is to just quickly show how to optimize, but not details of how this is done. So you can see you have similar structure, same elements. You have your delay. We're gonna call these delay elements, similar as my diagrams here. This is your coefficient getting multiplied. This is again a pipeline register here, and then a bunch of adders and more delays. And a significant difference between this one implementation and this one, no, this one is actually trash, but this one is that this one if you look at it, data is coming in parallel. This one, data is coming in serially. So the data comes in serial to all the blocks, and it gets propagated through as input data comes in until you get an output here. And again, these different section fits directly into DSP blocks. That means your input data will scale with DSP blocks. Your number of coefficients scales with the number of kernels, not elements, not CLBs and FPGAs. Another, I'm calling the drawback now, or limitation, is, but later on you will see it's not so much of a limitation. Depends on how you plan to implement this algorithm. This one, what they call a throughput, that means how long does it take to get an output data? 1, except you have two cycle of latency. You have 1 clock cycle throughput. That means if you put data on every clock cycle, you will get a data on every clock cycle at the output, but not so much for this one. This one requires what I call n number of clock cycles to get the output because of the nature of the structure. So that means if you have 9 kernel elements, your throughput is 9 clock cycles. Again, this might seem like a limitation, but the benefits that comes with this structure, it's worth taking the bullet. I'll go through this on this video or on the second video, depends how much I get into this. But this is pretty much how this optimization algorithm, how this algorithm will be optimized into the FPGA. We're going to use pipeline transposed FI filter. In the next video, we'll look at the VHDL design for this one, created by Mr. V on YouTube, and this one, which is also leveraging some code from Mr. D, also on YouTube. We'll look at how fast can we clock this one versus how fast can we clock this one in terms of resource. Where is this getting implemented? How is the tool dealing with this, with routing and implemented this one? Using this structure versus using the other structure. We'll run implementation and look at the output performance and the resource utilization of the two different structure. Thanks for watching, guys. I'll catch you later. Goodbye.